Alright, what's going on, you guys? Another LeetCode video today. This one's called Permutations. So we're given an array of nums of distinct integers, and they want us to return all of the possible permutations. And that those permutations can be returned in any order in a vector. So basically, so they're giving us, looking at input-output, they have nums here. It's an array of size 3, so there's three integer elements, and then they want us to return every permutation of those 3 elements. So something important to understand for this problem is when you have distinct, just a set of unique numbers of size n, there's going to be n factorial possible permutations. So that's just a combinatorics property. It's helpful to know for this problem. So the way I'm going to solve this is with recursive backtracking. So we know that if we take the example 1, 2, 3, we know that n is equal to 3. So we should be expecting n factorial size for our solution vector, or there should be n factorial permutations of this, right? Or 3 times 2 times 1, or also 6, right? So there's going to be 6 permutations for these 3 numbers. So for our recursion, we're basically going to start with an empty set, and then we're going to recursively add numbers to the set until we have all 6 solutions. So at first, we can add any number, right, to begin with. So because there's 3 options to choose from, so we're gonna have a branching factor of 3. And we're going to, so for example, we'd be here in the recursion, we can see our set is empty, so we can choose any number. So we'd add a 1, and then for backtracking, we'd remove this element from the vector and then take the next available option, which is 2, right? So then repeating that process for backtracking, we'd remove this 2 and then add the next available element, which is 3. Okay, so that's it for the second level there. So now our branching factor is going to decrease again. It's going to decrease by 1 at every level. So now when we're at this 1, we can only add a 2 or a 3 now, right? Because there's already a 1 here, and they have to be unique, right? The elements in the set for the permutation to be valid here. So so the next possible number we can add here is 2. So we'll add a 2 to the vector there, and then for backtracking, we'll pop the 2, add the next available number, which is 3. So that's it for that 1. And then, likewise, the rest of these nodes in this level are going to have a branching factor of 2. So we can add a 3 here, backtrack, pop the 3, and then add, actually the first available number there is going to be 1, technically speaking, because we're iterating forward through the array. So we're going to choose the 1 first, pop that, and then we'd add the 3. And then finally, for this 3, only 2 elements we can add here. It's either going to be the 2 or the 1. So let's add the 1 first, and then we're going to backtrack and add the 2. And then at this point, there's literally only 1 possible available option remaining, so it's pretty straightforward to finish off this algorithm. It's literally just going to be a matter of adding the last remaining element, right? So 1, 3, we can immediately see it's 2, and the way that's going to work algorithmically is I'm just going to use a find function, which is linear. So it is going to give us a little bit of a worse time complexity, but the runtime will still be pretty good. So just going through and adding the remaining elements here to each of these. So that's going to do it, and that's going to be, 6. We're going to have 6 different permutations here in the final vector of permutations, and that's going to be our answer. So in terms of the time and space complexity, our time complexity is going to be big O of n squared times n factorial. And this is because, usually when you're looking at time complexity for problems involving a tree, specifically recursive problems involving a recursive tree, you can look at the time complexity as, how many nodes do you have to visit in the recursive tree in the worst case? Well, for this type of tree, where our branching factor is decreasing by 1 at every node, and we know that the bottom level is going to have n factorial nodes, well, that's going to be approximately n times n factorial nodes in the total tree. It's not going to be exact, but it's a good approximation. And then we also have a little bit of extra work, right? Because at each one of these nodes, we have to look and say, okay, which nodes have we already added, right? Like which ones do we need to skip? So that's also going to cost n time potential in the worst case. So that's why it's n squared times n factorial for the time complexity. For the space complexity, we're going to have, it's just going to be big O of n, because our recursive call stack, this tree, has a depth of n, because at every level, we're basically building up these solution vectors, which are all of size 3. And that's, correspondent to n, right? Because n is 3 here. So, basically, it's just the height of the tree, which is n. So that's it for the time and space. Let's go ahead and implement this. So the first thing we need is a result vector. So I'll just call that res, short for result. We also need to make a vector to pass in for the current permutation. So it's just a vector of integers. I'll just call it perm. That's going to be of size 0 at first, and then maybe just for clarity, I'll also indicate that this is size 0 to begin with. So I'm going to overload this permute function by redefining it as a private function method. So let's call it there. We're not going to put values into it yet because we haven't written the signature, but we'll do that next. So we'll return res after we see that recursion and it runs all the way through. But let's define this function permute, or the function overload for permute. So we're gonna have permute, it's gonna take this result vector, so by reference, because it's kind of like a global. So we need that result vector. We need the current permutation array for the permutation we're building. This can be by reference. And then we finally need, so res perm, and then we need that array of nums that they give us so we know what options we're working with. So that's just gonna be a vector, another vector, or another vector of integers by reference. So for nums. Okay, so let's seed this now. So we're passing in res, perm, and then nums, just 3 parameters. Okay, so the first thing we want to do here is see if the array size of our permutation array, so perm.size is equal to nums.size, then we know we have finished with the permutation. So we can add, so we're going to do res.pushback to add the permutation array to our result array of those permutations. So perm, so that'll handle that, and then we're just going to return from the recursion because that's going to be like a leaf node. leaf node base case. So then otherwise, we're just going to loop through all of those options. So we're going to say for an I equals 0, while I is less than, let's see, it's going to be nums.size I++, because those are the options. So we're just looping through those options, and then we're going to check first to see if we've already added this number. So if we're going to say if find, so we're going to use the built-in find function on C++. This is linear, so that's why our time complexity was a little bit worse. So this is going to be find on nums begin, so that first iterator, and then nums array to the last iterator. So we're just looking through the whole nums array for nums I, and not the nums array, it's the, we're looking through the perms array, so for the permutation we're building. So, and it's just perm singular is what I called it. So in the perm array, from the beginning iterator to the end iterator, if nums I is in there, find will return to us, let's see, find should be not equal to the permutation array dot end. So basically, if it's found in there, if it's not found, it'll be equal to perm.end. But basically what this line is saying is that we already have this number inside of this permutation, so we don't want to add it again, right? Because all of the numbers in the array are distinct. So we're looking to skip over numbers we've already added. Okay, if we didn't add that number already, then we can go ahead with adding it to the permutation. So we'll just say perm.pushback nums I, and then we'll do the recursion. So we'll call it permute, and then push or pass in the result array, the current permutation, and then those nums input. Okay, and then we're gonna do backtracking, right? So we have to do perm.pop back, basically to remove the last number we just added, and then try the next available number. So that's pretty much it for the code. Let's go ahead and run this. So hopefully this video was helpful to you in understanding the problem better. If it was, leave a like and subscribe, and I'll see you guys in the next video. Peace.